Hello everyone, we will be starting with the condensation derivation where we left. So that is the local mass flow rate per unit width is given by gamma of y. So gamma of y equal to 0 to delta rho L V dx, because delta itself is a function of y, but at a given y we are integrating over complete x. So gamma of y equal to, substituting v, 0 to delta rho L g into rho L minus rho v upon mu L into delta squared x by delta minus half of x by delta whole squared dx. So g rho L into rho L minus rho v upon mu L delta squared into x squared by 2 delta minus half of x cube by 3 delta squared is what I get between the limits 0 to delta. Substituting rho L g rho L minus rho v upon mu L delta squared into delta by 2 minus delta by 6. So that is, this comes to delta by 3. So rho L g into rho L minus rho v delta cube divided by 3 mu L. So this is my gamma y. Now the net mass flow rate m dot equal to b of gamma of y, that is b is the width of the plate. So you have b rho L g into rho L minus rho v into delta cube divided by 3 mu L. So this is my mass flow rate. This is my mass flow rate. Now the next thing is, we will take the heat transfer problem. We will take up heat transfer problem. So that is, you have, if you take the energy equation, U del T by del X plus V del T by del Y equal to alpha del squared T by del X squared plus del squared T by del Y squared. This term is not important because the Y scaling is very large. Now we are saying that there is film velocity is very less, so we can neglect U and V, and del T by, if not definitely U, del T by del Y is negligibly small, because the film is negligible, because both the wall and the film are isothermal. Because of this, so this term is 0 because if U is 0, and we are neglecting because this is del T by del Y is 0. So now we have d square T by dx squared equal to 0, which implies dt by dx equal to C1, which implies T equal to C1x plus C2. So now what are the boundary conditions? At x equal to delta, T equal to T sat, and x equal to 0, T equal to T wall. So if x equal to T wall, which implies T wall equal to C2. Now this implies T sat equal to C1 into delta plus T wall. So C1 equal to T sat minus T wall by delta. So T equal to T sat minus T wall into x by delta plus T wall. This is my linear temperature profile. Okay, now if we take up the heat flux, so that is, if you take up the heat flux, that is heat flux into the wall, heat flux into the wall is equal to heat flux across the film. This is energy balance. So you have KL into T sat minus T wall upon delta is equal to H into T sat minus T wall. This is going to fetch me that H is equal to KL by delta, because T sat minus T wall gets cancelled out on both sides. So now we shall find thickness delta. To find thickness, that is gamma of y, we have already found m dot. So m dot we have found it as b gamma y, that is we have found this as b rho l g into rho l minus rho v delta q divided by 3 mu l. So now rate of condensation, if I want, dm dot divided by dy is equal to b rho l g into rho l minus rho v upon 3 mu l into 3 delta squared into d delta by dy. Remember, delta is a function of y. So you get, so this is what you get for dm dot. So dm dot is what you get, this equation. This dy gets cancelled out. So the rate of heat transfer from vapor to the plate through the film, that is dm dot hfg is equal to KL into bdy into T sat minus T wall upon delta. That is heat released by the vapor condensed and the rate of the heat transfer from the vapor to the plate through the liquid film. So you have dm dot divided by dy equal to KL into B upon HFG into T sat minus T wall by delta. So this is also one more equation for dm dot by dy. Comparing these two equations, both are same. So if you compare these two equations, so what is that I get is that, so you get b rho l into g into rho l minus rho v upon 3 mu l into 3 delta squared into d delta by dy is equal to KLB upon HFG into T sat minus T wall upon delta. So you get rho L G into, or let me write delta cube. If I put this delta cube d delta equal to directly d delta cube by delta equal to mu L KL into T sat minus T wall upon rho L G into rho L minus rho V into HFG. Please note B has gotten cancelled out into dy. If I integrate this, delta to the power of 4 upon 4 equal to mu L KL into T sat minus T wall upon rho L G into rho L minus rho V into HFG into y plus c. At y equal to 0, delta equal to 0, which implies c equal to 0. So you get delta of y is equal to 4 mu L KL T sat minus T wall upon rho L G into rho L minus rho V into HFG into y to the power of 1 by 4. So now we are in a position to calculate delta. So because we got delta, I will now be able to calculate H. That is, H is equal to KL by delta. H is equal to KL by delta. So rho L, so H you get as, if you substitute for delta, what we just now got for delta, if you just substitute here, you are just going to get this as rho L G into rho L minus rho V into HFG upon 4 mu L KL into Tsat minus T wall T into Y. Now KL is there and into Y is there in the denominator, and if you have KL which you have to push inside to the power of 1 by 4, so you have to multiply by KL to the power of 1, KL to the power of 4, so then you will end up getting, because it is 1 by 4. If you integrate this over length, complete length HL bar, that is 1 by L 0 to L H dy. If you integrate this, so rest all is common constants, that is rho L G into rho L minus rho V HFG KL cube, because KL to the power of 4 upon KL cube, 4 mu L Tsat minus T wall to the power of 1 by 4 into 1 by L integral of 0 to L y to the power of minus 1 by 4 dy. So you get this as HL bar equal to, that is 4 to the power of 1 by 4, everything if I just do, I get 0.943 into rho L into G into rho L minus rho V into HFG KL cube upon 4 mu L into Tsat minus T wall into L to the power of 1 by 4. That is, if you integrate this, you are going to get 3 by 4. All that has been subsumed into this. Okay. So one little small step I have skipped, but I guess you can integrate that and put that there here. So you get m dot equal to b gamma y, that is b of b gamma y, that is you have b rho L G into rho L minus rho V into delta cube divided by 3 mu L. But delta y, we know that it is 4 mu L KL to the power of 4 into Tsat minus T wall upon rho L G into rho L minus rho V. We have just derived this HFG into y to the power of 1 by 4. So if I substitute this, I am going to get m dot equal to b rho L G into rho L minus rho V upon 3 mu L into delta Q, that is same thing, all of this to the power of 3 by 4, that's all. So Tsat minus T wall upon rho L G into rho L minus rho V into HFG into y to the power of 3 by 4, because there is delta Q. So, and the properties are to be calculated at the film temperature, that is Tsat plus T wall divided by 2. So, we got, remember that this mass flow rate is a function of y. At every location, the mass flow rate is going to change. So, that's what we got for the mass flow rate. Now, let us take up effect of subcooling. We shall take up effect of subcooling. So, if we take effect of subcooling, the temperature profile is going to have curvature. If you recollect, I had plotted temperature versus x to have a curvature, but I had taken linear. To account for this additional, I take Rohesno gave this correction HFG prime equal to HFG plus 0.68. I am not giving the derivation. How did this 0.68 came? 0.68 CPL into Tsat minus T wall. This is a sensible heat, but only I am taking 0.68 times. So the same equations which we had calculated are valid, except that HFG has to be replaced by HFG prime, and the properties are again at TF equal to Tsat plus T wall by 1. And one thing I want to introduce, that is Jacob number CPL into Tsat, that is sensible heat upon latent heat. So HFG prime will be equal to 1 plus 0.68 1 plus 0.68 into Jacob number into HFG. This is what you will get this in terms of Jacob numbers. Now let us find out what is the Reynolds number, because that's what has to characterize whether my flow is laminar or wavy or turbulent. So I get Reynolds number equal to rho L um dH upon mu L. So um equal to mass flow rate per unit width upon rho L into delta. Okay, delta rho AV. So rho L into delta. So that is mass flow rate per unit width. So dH equal to 4 AC by P. Okay, so if you just take the film, so this is my width B, this is my delta. Okay, so is cross sectional area is 4 delta B, but interesting thing is here perimeter I am going to take only as B, because that is the only surface, that's the only, I should take actually maybe only B, not even delta, correct, because that's the only one which is contributing for the film condensation. So B gets cancelled out, so I end up getting my hydraulic diameter as 4 delta. So that's the key in this understanding. So RE equal to rho L, um is gamma by, that is mass flow rate per unit width, into delta into 4 delta by mu L. So that fetches you 4 gamma by mu L. Remember, gamma is a function of y. So gamma of y equal to rho L G into rho L minus rho V delta cube. We have derived this earlier, so I am just borrowing that. So you get, so if I make an assumption that rho L is very much greater than rho V, I can write RE equal to 4 gamma by mu L. If I substitute that, I write that 4 rho L squared G delta cube divided by 3 mu L squared, because one mu L here and another mu L here. So you get 4G delta cube divided by 3 nu L squared. So this is my Reynolds number. So now Reynolds number we have gotten. So delta equal to KL upon H. This is what we know, which implies that delta at y equal to L is equal to KL upon H at y equal to L, because that's, this equation is valid at any y. But only one small integration I am not doing, I am directly taking, that is H at y equal to L equal to 3 by 4 H average. So if you just see this equation which we have derived, from this equation you can derive it. See, this is the H equation, H dy. From this equation you can derive H at x equal to L. So that one little small step I am, this one do it yourself. That's an exercise I am leaving for you. So Reynolds number we had RE equal to 4, because I want what is the Reynolds number at the y equal to L, what is that which is coming out there. So 4G delta cube by 3 nu L squared, that is 4G by 3 nu L squared into delta cube. What is my delta cube? 4G by 3 nu L squared. Delta cube is KL by HY of L. So that is KL upon HY of L at y equal to L cube. So if I substitute 4G by 3 nu L squared KL upon 3 by 4 H average cube. So you get H average equal to 1.47 KL RE to the power of minus 1 by 3 G by nu L squared whole to the power of 1 by 3. So that means from the Reynolds number you can calculate H average, or you can calculate Reynolds number based on the H average. So this is how you can calculate for the flat plate. And now if you take a cylinder, can we just move on to slides please? If you move on to slides, so you have, as I said, this was the flare plate where we got perimeter as length, width of the plate, and cross sectional area as width into delta. And cylinder, if you take cylinder, this is my diameter, so you get P equal to pi d, and surface area is equal to pi d into delta. Pi d into delta, why? Because you have delta like this. So you take, this is the film which is coming out, so you take this area, cross section, not surface area, cross sectional area as pi d delta. Okay, so of course you can calculate AC by P, that is you get 4 AC by P, so you get 4 delta. Okay, so that is how you can calculate the hydraulic diameter. Now whatever we derived so far was only for laminar flow, but if I were to take wavy, the laminar flow, that is, if you just see this slide, in this slide you have H nu L squared G to the power of 1 by 3 upon KL, and this is Reynolds number. So you have laminar flow till a Reynolds number of 100, and wavy laminar you have between 100 to 1800, that is laminar you have between up to 100, and wavy laminar up to, that is 1100 to nearly 1800, and turbulent is Reynolds number beyond 1800. So if we go to laminar wavy, for laminar wavy the H vertical wavy is equal to REKL. This is without derivation I am stating, 1.08 RE to the power of 1.22 minus 5.2 into G by nu L squared to the power of 1 by 3. That is, this is valid between 30 to 1800, and rho V is considered as rho L, and we need RE. RE for vertical wavy. RE for vertical wavy is 4.81 plus 3.7 LKL into T sat minus T wall upon mu L HFG prime. This is not HFG, it is HFG prime into G by nu L squared to the power of 1 by 3. All this to the power of 0.82. Okay, so this is for vertical wavy. And vertical turbulent, if you have vertical turbulent, so you have H equal to REKL upon 8750 plus 58 Prandtl number to the power of minus 0.5 into RE to the power of 0.75 minus 253 into G by nu L squared to the power of 1 by 3. So this is one, and to get the calculate the Reynolds number, HL bar upon KL into nu L squared by G to the power of 1 by 3 REL to the power of minus 0.44 plus 5.82 into 10 to the power of minus 6 into REL to the power of 0.88 PR to the power of 1 by 3 whole of half. So how do I get my Reynolds number? If I know the average heat transfer coefficient, I know the Prandtl number, I know all the properties, I can solve this trial and error. But what in few textbooks they plot this, they call as B parameter. They plot this B as a function of this and get the, they plot REL as a function of this. So once you get this value, for a given value of this, what would be the REL for a given Prandtl number? If you have plotted and kept a graph, you can directly get it. If this is an inclined plate, if my plate is inclined, so if my plate is inclined, this is theta, this is where it is condensing, that is condensate is falling. So H inclined is equal to H vertical into cos theta. So same equations are valid. So we have derived for laminar, but I just stated directly for wavy without derivation H and RE vertical, and for vertical turbulent I have given the equation for H and average heat transfer coefficient. So with this actually we will be, so if we just spend a little time here, in this slide, the heat transfer coefficient is continuously decreasing with the increase of the Reynolds number, and the turbulent flow it goes on increasing, and naturally as the Prandtl number increases, the heat transfer coefficient also increases. So this is about the condensation. Just to take a quick recap, what did we do is that we first considered that we have laminar film condensation and laminar wavy, and turbulent, these are the three zones, and Reynolds number less than 30 is considered as laminar, 30 to 1800 is considered as wavy, and Reynolds number greater than 1800 is turbulent. We derived a relation for film thickness, the mass flow rate as a function of y, delta as a function of y, h as a function of y, derived for the laminar flow. But major assumption what we have taken is del V by del X equal to 0, that is interfacial shear stress is 0. There is going to be, if we just put air around this flat plate, that is the condensate, what they call, the heat transfer coefficient is going to change completely. So the presence of condensate around the flat plate is going to deteriorate my heat transfer coefficient. Seriously, how it will affect is a major study by itself. In nuclear industry, this is what is a major study what they are worried about. So because of the presence of the condensate, air or gases, so the heat transfer coefficient is going to get seriously affected. So they do measure it, and of course one can do derivation relaxing this interfacial shear stress and calculate the H, but at undergraduate level it would be little tough for them to grasp it. So it would be too much to teach, not that tough to grasp. They will understand if we teach, but because of the lack of time we would not be able to teach. What I will do is in the tutorials, so in the assignments, I am going to give you some problems. Because of lack of time I am not going to do here. I am going to give some problems for laminar, laminar wavy and turbulent, so that you get the feel of how to calculate the mass flow rate and the heat transfer coefficient. Thank you.